The article of the day is You Can't Sacrifice Partition Tolerance. In 2000, Dr. Eric Brewer gave a keynote at the proceedings of the annual ASIM Symposium on Principles of Distributed Computing, in which he laid out his famous CAP theorem, that is, a shared data system can have at most two of the three following properties: consistency, availability, and tolerance to network partitions. In 2002, Gilbert and Lynch converted Brewer's conjecture into a more formal definition with an informal proof. As far as author can tell, it's been misunderstood ever since. On consistency, atomic or linearizable consistency is the condition expected by most web services today. Under this consistency guarantee, there must exist a total order on all operations such that each operation looks as if it were completed at a single instance. This is equivalent to requiring request of the distributed shared memory to act as if they were executing on a single node responding to operations one at a time. Most people seem to understand this, but it bears repetition. A system is consistent if an update is applied to all relevant nodes at the same logical time. Among other things, this means that standard database replication is not strongly consistent. As anyone whose read replicas have drifted from the master knows, special logic must be introduced to handle replication lag. On availability, for a distributed system to be continuously available, every request received by a non-failing node in the system must result in a response. That is, any algorithm used by the service must eventually terminate, qualified by the need for partition tolerance. This can be seen as a strong definition of availability even when severe network failures occur. Every request must terminate. Despite the notion of 100% uptime as much as possible, there are limits of availability. If you have a single piece of data on 5 nodes and all 5 nodes die, the data is gone, and any request which required it in order to be processed cannot be handled. On partition tolerance, in order to model partition tolerance, the network will be allowed to lose arbitrarily many messages sent from one node to another. When a network is partitioned, all messages sent from nodes in one component of the partition to nodes in another components are lost, and any pattern of message loss can be modeled as a temporary partition separating the communicating nodes at the exact instant the message is lost. Some systems cannot be partitioned. Single node systems, that is a monolithic Oracle server with no replication, are incapable of experiencing a network partition. But practically speaking, these are rare. Add remote clients to the monolithic Oracle server and you get a distributed system which can experience a network partition, that is, the Oracle server becomes unavailable. For a distributed, that is multi-node system to not require partition tolerance, it would have to run on a network which is guaranteed to never drop messages or even deliver them late, and whose nodes are guaranteed to never die. You and I do not work with these type of systems because they do not exist. Choosing consistency over availability. If a system chooses to provide consistency over availability in the presence of partitions, again, read failures, it will preserve the guarantees of its atomic reads and writes by refusing to respond to some request. It may decide to shut down entirely, like the clients of a single node data store, refuse writes like two-phase commit, or only respond to reads and writes for pieces of data whose master node is inside the partition component, like memories. This is perfectly reasonable. There are plenty of things like atomic counters, for one, which are made much easier or even possible by strongly consistent systems. There are perfectly valid type of tools for satisfying a particular set of business requirements. Choosing availability over consistency. If a system chooses to provide availability over consistency in the presence of partitions, altogether now failures, it will respond to all requests, potentially returning stale reads and accepting conflicting writes. These inconsistencies are often resolved by causal ordering mechanisms like vector clocks and application-specific conflict resolution procedures. Dynamo systems usually offer both of these, Cassandra's hard-coded last writer wins conflict resolution being the main exception. Again, this is perfectly reasonable. There are plenty of data models which are amenable to conflict resolution and for which stale reads are acceptable, and for which unavailability results in massive bottom line losses, like Amazon's shopping cart system is a canonical example of a Dynamo model. But never both. You cannot, however, choose both consistency and availability in a distributed system. As a thought experiment, imagine a distributed system which keeps track of single piece of data using 3 nodes A, B, and C, and claims to be both consistent and available in the face of network partitions. Misfortune strikes and the system is partitioned into 2 components A, B, and C. In this state, a write request arrives at node C to update the single piece of data. Now, that node only has 2 options, that is, accept the write, knowing that either A and B will know about this new data until the partition heals. Second, refuse the write, knowing that the client might not be able to contact A and B until the partition heals. So, to conclude, you either choose availability, that is door number 1, or choose consistency, that is door number 2, but you cannot choose both. To claim to do so is claiming either the system operates on a single node and therefore is not distributed, or that an update applied to a node in one component of a network partition will also be applied to another node in different partition component magically. Now, a readjustment in focus. Brewer wisdom, that is yield and harvest, which comes from Fox and Brewer's harvest, yield, and scalable tolerant systems. Here we assume that clients make queries to servers, in which case there are at least two metrics for correct behavior: yield, which is the probability of completing a request, and harvest, which measures the fraction of data reflected in the response, that is completeness of the answer to the query. On yield, numerically this is typically very close to uptime, but it is more useful in practice because it directly maps the user experience and because it correctly reflects that not all seconds have equal value. Being down for a second when there are no queries has no impact on users or yield but reduces uptime. Similarly, being down for 1 second at peak and off peak times generate the same uptime but vastly different yields because there might be an order of magnitude difference in load between the peak second and the minimum load second. Therefore, we focus on yield rather than uptime. On harvest is far more overlooked metrics, especially in the age of relational databases. If we imagine working on a search engine, however, we can imagine that on being separate indexes for each word. The index for web page which uses the word cute is on node A, the index of the web page which uses the word baby is on the node B, and the index for the word animals is on the node C. A search then for a cute baby animals which combined results from node A, B, C would have 100% harvest. If node B was unavailable, however, we might return a result or just cute animals, which might be a harvest of 66%. In other words, harvest is equal to data available by total data. So here's the TLDR of the CAP theorems: consistency, availability, and partition tolerance. Partition tolerance is mandatory in distributed systems. You cannot choose it. Instead of CAP, you should think about your availability in terms of yield, percentage of requests answered successfully, and harvest, percentage of required data actually included in the responses, and which of these two your system will sacrifice when failures happen.